All right, we're on. Welcome to the unannounced live stream. It's just like, hey, you know what? I have a couple hours. Let's just do it. Hey, welcome to my show. I Can Science That. We're here with Alan, who's been a frequent guest of the stream, and he inspired me to do the work we're going to talk about today. And a new guest, Toby Walker. Toby, you want to introduce yourself?
Yeah, sure. My name's Toby Walker. My background is mostly in computer science and computer information security, but I have recently started to dig into a lot of the claims of special relativity and trying to kind of unwind all of that. There's a lot of cognitive dissonance for me there with things like the twin paradox and particle wave duality and things like that. So I'm trying to unwind all of that, and as part of doing all that, there's also this flat Earth thing that's getting really big. And so I was able to actually unwind all of that by accepting the idea of a geocentric stationary plane, basically.
Very interesting. Very interesting. Those are really intriguing topics, I think, for many people. I'd love to talk about any of those things. So this should be fun. So you're happy with the geocentric flat Earth model as your solution to all of this? That's right?
Yeah.
Geocentric, but not flat.
No, flat.
Flat. Okay. Cool. Because that's the model that I built after having talked to Alan about this. So that's what I'm doing today. Is we've talked before about what evidence there is, what raw data we have, and how we can apply that into build a model, right? And so that's what I did is so there's no mistake. I don't believe in the flat Earth or the stationary models, but that doesn't mean I can't entertain it and I can't explore the possibility. So that's what I've done is I built one. I built a model based on the data, and it's surprisingly close to what Alan said it would be. So that's really amazing. And I'll show that as soon as he's back. We lost him.
Yeah, it looked like he was trying to mess around with ability to present or something like that, I'm assuming.
Cool. Yeah, you know what? I can start the presentation. He'll show up in a minute, right? Let's just. So. He wants to see it though. So I guess we could talk about computer science. I do computer science myself, cool. And I found something interesting. You might have a take on this. I have discovered that a lot of the debunker community seems to come from computer science, a programming background. What do you think about that?
Yeah, I would say, my aspect is actually more engineering side. I was a DevOps engineer, so kind of walking that line between architecture and data science, or not data science, but systems engineering. So I actually think my theory is actually that systems engineers in general, are the ones that become skeptical of this because they have to look at things in a functional, dynamic way. Kinematics doesn't mean anything when you have to actually get into dynamic effects and make something work. And yeah.
That's interesting. Yeah, I can see that. As an engineer myself, I've gotten into some weird philosophical arguments with physicists just from our different point of view on things. And people get really stuck in their point of view sometimes and comes up with arguments that even when we fundamentally agree on stuff, it's intriguing. But yeah, I think there's something to that. So welcome back, Alan. We're all set. Hey. If you guys are ready, I will present my screen. Let's see here.
Yeah, absolutely. Screen. And before we begin, I wanted to say thank you for going through this. This is so cool of you, man, because when I first met you, you were like, no, there's no Aether. Like, you weren't even interested in it. And for you to even like do this, like just to see how it would work is so cool, man. I really appreciate it. Like, so hats off to you. Much love and respect, man.
Yeah, I mean,
this is awesome.
I'm still gonna emphasize. I'm not saying that this is my proposal for what I think the world is.
No, absolutely.
Right. This is me saying, if you want it to work, this is what you have to do.
Hey, we appreciate the help, man, and so.
I mean, it's all theories, right? All of it. So at the end of the day, I would never claim this as reality either, but I really appreciate you putting forth this theoretical framework.
Okay. And so this is my model of how the ether would have to flow over the flat Earth in order to get optical gyroscopes specifically to work the way that we understand that they do. And we can talk about what exactly that is in a bit. But I wanted to start with, cut straight to the chase, which was Alan had told me that he expected to find an east to west flow. And lo and behold, what do we got but a ginormous east to west flow? Much more so than I expected to see. So any comments about that from you guys? Can you see this okay?
No, it looks good, man.
Okay. I do expect there'll be some people in the chat or viewing later that are thinking what I was thinking when I started this all out, which is that it can't be a uniform east to west flow, because what we need to get right from the gyroscopes is a tilted flow. And Alan, you and I have talked about that before, and I have some demos of what that looks like that we should show. But first, let's look at why it is what it is. This is a tilted flow. And you can kind of see that better if we get down in here and look. Let's see if I maybe zoom in a little. I don't know. There's so much noise on here. It's kind of hard to see. But if we look at these arrows, can you see my pointer? I think you can.
Yep.
This arrow is longer than this arrow, right? And so what we're seeing is that at surface level, there's an east to west flow. But that flow must accelerate, must get faster as you get away upwards from the surface. And it continues even underneath the surface, right, getting slower down there. So what that creates then is, since the flow is faster up high and slower down below, since the flow is faster up high and slower down below, that creates a net circulation in the vertical plane, right? So at the equator, that would, in a gyroscope, that would create a rotation in this plane, like the vertical plane, right? However, up at the pole, up the North Pole, we don't have that. We have, in fact, I started with the assumption that there was zero flow at the North Pole. I have no reason to say that, but I needed a starting point.
Right.
So I just made no flow at the North Pole, but there's a uniform circulation going around the North Pole. And that creates just a pure rotation in the horizontal plane. So what we see is that kicks the whole thing off with a pure rotation east to west at the North Pole. And then as you go outwards, that amount of rotation has to maintain steady, but then we have to create a wind shear, if you will. There has to be like a greater ether flow at high altitude in order to create the rotation in the circulation that we get. And then as you continue going out, all the way out, it reverses and the flow actually goes the opposite direction.
Oh, dude, that's cool.
In this just weird twisted vortex kind of a result.
So it kind of maps out a toroid naturally in that regard then.
Yeah, I expected it to look more toroidal than this. It's a vortex that's going this way, and it's got this shear layer that's accelerated flow up high, and then that flips over and the whole thing becomes an up and down flow at the edges, and then completely reverses outside that.
What is the source data here?
Yes, excellent question. What is the source data? Let's start there. Let's see here. Let's start with, I got to remember what I named all these things. I didn't even give them names. I think ether rotation. Yeah, whatever, say. Is this the one? I think this is the one. Okay, here's the source data. This is what we measure literally on the globe, which is that the gyroscopic rotation measured by, Bob's famous 15 degrees per hour. That's what it looks like. Is like Bob was over here in the West Coast of the United States, and this is what he measured: 15 degrees per hour, tilted to the surface like so. Bob measured that one. And somebody else, Alan, had found 3. Somebody was over here, I think in Russia, and somebody in Europe. I don't remember exactly.
Yeah, they were all right around the 45th lat, and then someone in Canada. The other 2 were in Europe.
Yeah. So based on that, Alan and I had agreed that at least up here in the northern hemisphere, at least at like the 45th latitude, that we should get something that looks like that. And the obvious answer, I would say the obvious, maybe it's not obvious to you guys, but it seems obvious to me, is this: that there is only one rotation, and the curve, the globe shape of the Earth explains why there's a tilt of that rotation relative to the surface, right? That up here, it's flat to the surface. And down here at the equator, it's perpendicular to the surface. And that seems very intuitive if you just imagine there is only one rotation.
But that's going off of just those 3 data points you guys had?
Well, no, that's going off of, for me, that's going off of the world's known data set, that this is known.
Yeah, it's for me, it's taken like the what we know was measured and like confirmed in the north, right? And then just giving the benefit of symmetrical to the globe to, and all that stuff, because it's about the flow, right? So what these measuring with the rotation or relative to the axis of rotation of the Earth would just be, we would equate it to the direction of flow from the ether in the sky. So
okay, well, the only reason I bring it up is just because I'm curious about the flow in the south, and specifically because the flow that we get, the measurements of flow that we get, come from satellites, which then are already extrapolated to the GCS, so or interpreted by the GCS. So as far as applying that to a flat model, there may be some incongruency there, but in any case, I see what you're saying.
Right. So to sum up that question, I take it basically as a given at this point that this is the way the flow goes. As far as hard data, we have, Alan has agreed to the 3. Those are all right about the 45th parallel, and they happen to match this data set. So we have no reason to specifically contradict this data set. And so I figured it's safe to run with it.
Yeah, we're just modeling a theory. I totally hear you. Yeah.
I would also add, this is the same rotation that you get with a Foucault pendulum. It's the same you get with a gyro compass. It's the same you get with a mechanical gyroscope. So if it were different than this, a lot of people around the world would be very confused.
Well, the levels, we don't need to go into the weeds on that. I don't want to.
Yeah, we don't have to get into the weeds, particularly if you want to contradict it. I'm happy to look at any contradictory evidence. We just don't have any at the moment. So we needed something to go with. And this is consistent. We've agreed at least for, Bob Nodell's and the 3 versions that, that Alan found. Okay, and let me hit this little slider and show you what I love about this little sim is that,
oh, dude, that's nuts. I love it.
Is we could take it and we can just unroll it and make it flat and look at what those rotations look like. Those same measurements would look like on a flat plane. And here they are. And we can see this is, like Bob Nodell's finding his 15, but it's not parallel to the surface, and it's not perpendicular to the surface. It's at an angle. Right. And those 3 that Alan mentioned would be at the same 45-degree angle to the surface. And so those, I think we can agree on, are definitely the way it must be. And then these are extrapolated from that based on, acceptance of mainstream data.
At a consistent altitude.
Yeah, I mean, at this scale, it's certainly safe to assume we're at sea level with all of these.
Okay.
There's the only suggestion that things would vary with altitude I've ever heard came from Bob. That was an interesting observation, but we don't really have much to go on there other than that one. If you have something else, maybe.
Well, I know
Yuri Galev.
Yeah. Oh yeah, Yuri Galev. Actually, that's a really good one because that's a
Does he suggest a different rotation at different altitudes?
No, he took measurements at different altitudes in the north, and he found varying speeds at altitude.
Varying linear speeds, varying rotational speeds.
Yeah. So he was taking radio signals and doing it. He didn't have a gyro.
Okay.
So
yeah, I'm only considering rotation at this point.
Gotcha. Oh, okay, bet.
Yeah, the idea is to come to an agreement between us that this is our best guess at what the rotation should be doing, and we have firm verification of this in certain places. Mm-hmm. So we agree to that, and then to ask the question: well, if that is correct, what must the flow do to create a circulation that looks like this? And then we could go and compare that with measurements of what the flow actually is, presumably.
Yeah.
Cool, right? I think it's pretty cool. This is a cool.
Yeah, it's really cool.
And
it's really cool. Yeah, it's really awesome.
Okay, so yeah, that's where I got that from. And so then what did I do next? Was I guess I could. Well, I mean, I made this one, which is kind of a visualization attempt at what that would be. Where in order to get the circulation like at the equator to be vertical, that means we need counter-rotating flows above and below the point of measurement. And so this is my visualization of that, where we have the counter-rotating, but here in the North Pole, those counter-rotations have coincided at the same altitude, basically. They come together to where you only get the rotation in the one direction, and then it kind of comes outward from there, as if it's rising up, as if the...
like a tornado stem coming, or you know what I mean, coming down? So
yeah, like there's a counterclockwise flow that comes to a pitch point at the North Pole, and then it rises up as it goes out away from the North Pole. Let's pull us away. It rises up off the surface and then comes back down again on the outer side. And meanwhile, there's a counter-rotating flow that's sort of doing the same kind of thing. So it's like a curved, if you took, you know how like a clutch plate works? Or like an automatic transmission where you have two plates in there and they spin inside a fluid.
Oh, I see. Yeah. And
that creates this shear. And if those plates were not flat, but in fact curved, you could make a curve to those plates to create the odd circulation pattern that we had. And let's see. And yeah, ultimately, this is the one I was showing you guys before. And what this is, this one takes a long time to run. What this one is then, is it takes those rotations that we agreed on, and then it calculates, and the boundary condition I started with, which is a zero flow at the North Pole. And then it says, in order to get the circulation in the adjacent cells, what kind of flow would have to be there. So for example, at the North Pole, to get a circulation going this way, we need flow, this way on this side and this way on that side. And so it just applies that amount of flow to the adjacent cells and then works outward from there and says, okay, but in this cell, there's supposed to be a little bit of a tilt to the flow. And so we're going to get the tilt by applying a little bit of up and down and side to side and whatever. And I let that run and iterate over several iterations until it finally gels into this pattern that we see here. And so, yeah, if we think that the reason for optical gyros is ether flowing, this is what the flow would have to be doing.
Mm-hmm.
And there's somebody at the door, so I will let you guys take it and have a little discussion. I'll be right back.
Yep.
Okay, I'll be right back.
Yep, no worries. Dude, the toroidal map. I'm gonna show him the when he gets back.
The pulsating toroid one.
Yeah, I think that's it, man. That's so cool. That's awesome.
Yeah, to me, it's a pretty satisfying interpretation as far as the shape goes. I still have a lot of questions about altitude and the south, but yeah.
Yeah, it's not bad for.
Oh, dude, it's
yeah,
that's not just like a 10-minute project. Someone that's actually willing to do the thought experiment. Like why should we be afraid to do a thought experiment?
Where is man? I can't find my ether vortex thing when I need it.
Hey, I'm back.
Hey, welcome back.
It was Amazon. My hard drive came.
Oh, nice. Did you get M. something? I hope, right?
It's an SSD.
All right, I'll allow it.
I don't know. My hard drive went down this week, and that's rough. All my hard drives are like over 10 years old, so
I also need to step away for just 1 second, but
okay.
You can continue.
All right, cool. I'm scanning through the text to see if there's anything interesting here.
Oh, here we go. Hey, can I present real quick?
Yeah, take it away. I think you have permission, right?
I don't know. Let me request.
Let me see.
Share screen, entire screen. There we go.
Guests. Is it giving you permission? Oh, yeah, it was right here. Add it to stage. There you are.
Yep, cool. All right. So what you were talking about earlier, I think the original model that this was based off of I went back and watched your video because this was like months ago when I kind of came up with this for the Aether one model. I went back and watched your video on it, and I agreed that the gyroscopic readings, like if we're going to absorb the actual measurements and not call it a parlor trick and acknowledge it for what it is and all that, you can't be like it can't not align with how it works on the globe, right? On the globe model, right? So obviously, trying to fit that in with the limited understanding of the ether and stuff that I had at the time, it was like this is kind of what I came up with to represent that. So it's like that toroidal flow that you kind of mapped out there. That starts in the center with the east-west, and then in the outer donut it diverges. So it's really cool that that actually turned out to be a viable model. So it was like nice, because then I started looking into toroidal stuff a lot more, and I think a toroidal field situation is a much more viable explanation for the realm that we live in, which I'll get more into that, but that's for like another discussion. But yeah, it's all very cool, and I'm so happy that you made that model. It's awesome. Thank you.
I'm glad you like it. Hopefully everybody understands it. Rob was saying he didn't quite get the gist on his phone looking at what the heck it was. It's not that complex of a flow, but it's dominated by an east to west circulation around the surface. And what creates the twist is that the rate of east to westedness varies with altitude. So we would expect to get faster east to west flow, or maybe more east to west flow higher and less east to west flow lower. And then that creates the circulation we need. And then the pattern, the specific pattern of how that varies would have to be set up very specifically to get the details of how it works. As far as why that should happen, I don't think anyone has proposed any why for that. Why would that happen? How the ether couples with mass energy. I think the presumption we're working with here is that ether would be this medium through which electromagnetic radiation travels. And so if the ether is flowing, that speed must be added to the speed of electromagnetic waves.
Yes, sir.
Right? That's the definition, as I understand it, of what ether is.
That's a huge part of it.
Huge
part of it.
Yeah, and then some people are like, "Is this a viable?" Well, and that's what it would be.
Yeah, dude. It's just a model, man. Like
it's
no different than other models that are presented. In my opinion. So, but it's cool, man. But
it's obviously much more complex than the globe model. The globe model with ether, I should say, if there's an ether, to get the same rotation with ether on a globe is trivial. All you do is that's just one rotation uniformly going around.
Just spin that globe, yeah.
Well, or hold the ether still. Yeah, this is something, Occam's razor comes in here and we say, well, we could just hold the ether completely still, make the Earth a globe, and rotate at a constant rate. Done. It works, right? Or we can roll it out flat, and now the ether, and hold it still, and now the ether has to do the flowing, and it has to flow in this complicated way. So, Occam's razor definitely suggests the other one's simpler, but there's no reason to say we couldn't possibly have this based on just this discussion here, right?
Mm-hmm. Yeah.
All right, cool. Anything you guys want to add or subtract?
No, just so in terms of complications, so like the natural ether flow, if it's taken that toroidal shape, that toroid, that vortex shape is the natural geometric expression of pressure mediation. So like when you look at a tornado and how it's formed and all that kind of stuff, you see it naturally form. So like if we, because I kind of think, because I'm taking it to a different level of understanding with it. Like I think that that it's more like of a toroidal pulse that we live in. So like that 15 degree per hour measurement is like a pulse rate of the ether that we exist in, and there's there's obviously like a flow within that, but it's not necessarily even like a wind motion. Like I really as I'm learning new things and reading old papers and old texts and books and stuff about it, like because I went from having that rigid view that it's like a solid rotation and stuff, and because it's just like as you learn more things mechanically about how it works, you have to adjust and stuff. So as I'm learning more about it, it's it's my favorite subject now. So thank you for putting that forward. Those are awesome visuals, man. I really appreciate it.
Yeah, that was really awesome visuals for sure.
Cool. And it also, the other thing I keep coming back to is, how do I test it? Right. Mm-hmm. This is just a model. The model is no good unless it creates a testable prediction. Right. You guys have any thoughts about how to proceed with testing these predictions or making predictions from it?
Yeah. So there's a ether book that I wanted to get you interested in to see if you would take a look at it. Because I don't know if you've seen on my channel, I had Robert Bennett come through, who's been studying the ether and this book in particular for a number of years. So he put together some like a whole kinematic model, basically, based off of this guy named Atsukovsky, who's been culminating all this ether research and stuff, and put together like an actual model in the sense of like he like re-examined all the measurements that are from experiments that prove like, you know, this or that about quantum and certain particles and that, and just kind of reinterpreted it as a vortexual ether flow.
Okay.
And yeah, it came up with a bunch of stuff. So I was gonna have you take a look at that and see what your thoughts were on it. But I have to go back and I have the numbers, but I want to go back and get the experiments that correspond to them too, so that you're not just pissing in the wind with a 600-page book. So
yeah, that's a lot. That's a lot for me, to be honest.
Yeah. So don't worry. Like I'm gonna when I bring it to you, it'll be coherent. So but yeah, I've got some stuff for you to look at to go over. Yeah, there's all kinds of stuff out there, man. It's just not really talked about.
Yeah, and you know, I mean, we could debate why that is, but I think it would be, for me, I'm going to say, I won't speak for you. I'll speak for me. For me, I'll tell you why I don't pay much attention to it, and it's because it's fringe, and the fringe rarely contains what history decides is correct. You know, sometimes history says the fringe is right. Like Einstein was fringe at first, but history ultimately decided, yeah, I think he was right. And so that's what we kind of focus on. It wouldn't make sense to take every homeless crackpot off the street and ask him what he thinks ether is, right? That wouldn't be a good approach, right? I think you'd agree with that. Mm-hmm. So we do have to cut it off at some point. Who do we want to spend our time focusing on, and who do we not? And yeah, that's a good question. I think actually Professor Rob is planning a talk on that this Sunday. He told me something about that.
Yeah. Well, in that respect, I would say that at the highest levels of particle physics, when you go to the Fermi lab and you look at the muon GS-2 or whatever it's called, like they say in the little excerpt there that everything is a sea of virtual particles and stuff. So like there's definitely a field that has physicality to it. The mathematical abstractions that are attributed to it to describe phenomenon are just kind of ignoring the fact that there's an actual physical field. And I think that that's a mistake, and I think that it'll come back, you know, so it already has. It's just described it in mathematic terms with no physicality to it. So.
Okay. Yeah, I mean, I keep my mind open. I want to recognize, and sort of one of my messages, I think, is that science is never really settled. We're constantly investigating and looking for new answers to the questions we haven't completely answered yet, right?
Yeah.
And so once in a while we discover something that we thought for sure, germs just, or not germs, flies. Like we thought for sure flies just spontaneously popped out of meat, right? And till somebody found out, no, that's not how it works, right? The flies lay the eggs hatch. That's how this whole thing goes down. And eventually, year on year, we pass that knowledge forward and we get smarter and smarter. And we learn more and more. And hopefully that's how it works. And someday, maybe somebody will come around with something and radically change our thoughts on ether and relativity and so forth.
Yeah. Someday soon, man. Come into a nearby future soon, or whatever, they say, or theater near you. All right. Cool, man. Well, I appreciate your time. Thank you, man.
Yeah, thanks a bunch. This was really cool. Really appreciate your time, Matt.
Cool. And if you guys are still on here, Rob and Clive, and anyone else, there was that paper that Alan had sent me. I thought it might be a fun topic to get together and go through, if you guys want to, about. I don't think it's related to the topic. Alan, you had said, you remember the one I'm talking about? You had said it was something that sort of backs up an east to west bias to the flow. Is this making any sense to you?
Yeah, Paul Marmot.
That's the one, Marmot. Yeah.
Yeah. So there was a couple papers I sent you. It was 1 second here.
I'm just going through them one at a time, really.
Yeah, I got you. Looking up. So let's see here. We got Paul Marmot, GPS and the constant velocity of light. Stephen Gift, the light transmissions and the Sagnac effect on a rotating Earth. And Stephen Gift again, GPS and the one-way speed of light. And I think that's it.
Okay, cool.
For GPS, yeah.
Yep, haven't read it yet, but I am down to go through it live. Grading sucks. Word. I haven't started grading yet. I still have some finals to do. I start tomorrow. Yep. Okay. Cool. Let's see if we can make that happen. And anything else you guys want to do as closing statements?
No. Is it all right if I shout out my channel?
Yeah. Oh, yes, please. Please.
If anyone's interested in, specifically, we do talk about flat Earth, but it's not specific just to flat Earth. We have PhD Robert Bennett there the last 4 weeks. He's a geocentrist, but not a flat earther, or at least that's his model. So, it's not confined to just that. But if you want to talk about ether flow, you want to talk about relativity, you want to talk about space time, you want to talk about Higgs boson fields, whatever, anything you have questions about, the current paradigm, that's what we're there for. So we have a Discord server. We meet every Tuesday at 7 p.m. Eastern. Yeah.
Can we put the channel link in the chat? Yeah. Can you do that?
Yeah.
Oh, you got that, Alan?
Throw your link in the chat, and if it won't let you, throw it in the private, and I'll copy it down. And while you're doing that, anything else like relativity related? You mentioned some interesting things. Anything you wanted to discuss, like the twin paradox, or I don't know, anything like that?
Actually, yeah. So I guess I would just ask, what is your best evidence of the constancy of the speed of light?
Let's see. One of my colleagues was explaining that my best evidence is going to vary depending on who I'm talking to. So I'll just say for myself.
Can we get the full gambit too, though? In addition to just your, the full spectrum. Hit us with it all.
I'd say I'll start with Maxwell's equations. Maxwell's equations work. Electronics work. And they don't include anything about the movement of a medium or the movement relative to each other or anything like that. And it seems like they would have to if that was relevant, or else it wouldn't work. So I'd start there. And then after that, I would say the Michelson-Morley experiment is next. And I don't mean specifically just Michelson-Morley. I mean the experiment that they designed, the apparatus, which I've actually seen in the classroom performed. And yeah, it doesn't change. So
then, I mean, I'm assuming you're familiar with Ruyang Wang's work in 2004 then, since you talked with Alan?
I looked it over. Yeah. And he doesn't indicate anything that contradicts what I just said. Wang does not show that there is a difference in the speed of light.
Okay, but if there was a linearization of the Sagnac effect, then wouldn't that mean that the Michelson-Morley experiment should have actually detected orbital velocity?
Yes, if there was, but mainstream says there is not. That
okay,
Wang is
but you acknowledge that
wrong.
At least Wang's experiment seemed to indicate that, right?
No, actually, I don't. I don't agree.
Okay, well, what is your contention on that?
That Wang missed some very obvious stuff.
Such as?
That's what I would say. His core is that seem to be, and maybe we're talking about different papers, seem to be that fast-moving missiles don't take their own speed into account when doing GPS calculations.
No, he's talking about a different paper. He's talking about the hold on one second. I can share if you want.
He claims that the Sagnac one, where there's no gap between the thing, and he's showing that there's a fringe created by
with a linear motion of the gyroscopic of the gyro, essentially, or the
Alan's sharing. Yeah, I'd have to look at it again.
Yeah, so this was different configurations of a gyroscope.
Did not measure any such thing, but I'd have to look at it again. That wasn't the one I was focused on at the time.
I'd be super curious to hear your input.
Yeah, I should look at it again. I think it would be much more interesting, instead of whatever he's doing, is to make a figure 8, which he actually shows there as E. Just do it with a figure 8. Static. You don't have to move it linearly. Just do a figure 8. And tell me what you get. And then do it with the racetrack C and tell me what you get there. You know, if you're going to build this thing, just build those two. Done, right? You don't need all the complicated stuff.
So let me ask.
I think it's telling that we don't have that data. So, you know.
Right. Let me ask you a question. So there's a fiber optic gyro mounted on this right here, and this is this. Oh, yeah. So this one says mechanical conveyor, but in 2004 he did the same thing with an air conveyor, so it's frictionless or whatever. So so anyway, the linear pull of this when it's rotating, right? It pulls on this, right? So it drags it across that air conveyor, and it fully detects that linear motion. It's not supposed to do that, right? Is that honestly the situation there?
I don't know. Because a fiber optic gyro,
because it fully
measuring something under constant linear velocity doesn't make any sense to me. But maybe I'm overlooking something.
Yeah. So it measures that, and then also in this loop here, this configuration, the rotational bits and the linear motion bits fully contribute to the fringe pattern. And that's where he was talking about the equation that he used to derive all that for the linear bit. He was like, oh, this is actually interchangeable with the circular derivation where they just change the length to the angular rotation speed, and then the area of the device.
I'll look at it again. If you have a particular paper, I have them all, I think, but if you tell me which one it is, I'll look at that.
Yeah, I'll send you these two again, because these are pretty pivotal here, I think. I'll send you some
I started at the top of the list, as I always do, right? And so I focused on the GPS stuff.
Yeah.
Which, as I was saying, is just really pretty bad.
Well, this is one that I sent you a while ago, and you said that you thought that Wang was joking around.
Oh, yeah, and there's stuff in here. Another thing, there's stuff in here that's completely inconsistent with what you have told me that you believe.
What did I tell you?
It feels like maybe we're kind of picking and choosing. You know what I mean? I mean, like, one of Wang's papers, as I recall, is about the one-way speed of light, and as you guys mentioned that as well. I think
that's a GIF paper. I think, but yeah,
he's proposing that speed of light is different in different directions, and it doesn't mean east and west. It means outgoing and incoming, right? Which is a bridge too far for most people.
Well, even Einstein just kind of said, we can assume it, but he never really substantiated that assumption.
Well, we can't prove it and we can't test it.
Yeah.
So it seems rather silly to even entertain something we cannot test. But it was one of the foundational.
Well, then doesn't that go the other way too?
It's like, what?
Sorry to interrupt.
Oh no, does it go the other way? Like,
so because you can't falsify the other one either, right? So,
well, if we can't falsify it, we can't reject it, and so I think it's worth admitting that we can't reject it. But I cannot reject that the world was created last Tuesday. I can't falsify that, but I'm not going to spend a lot of time entertaining it either. You know what I mean?
Dude, last Tuesday theory is one of my favorite theories, or whatever. When you told me that, I was like, no way, you guys actually.
Are you a last Tuesdayist now?
No,
you could be a last Tuesdayist, right? The idea is that right? Every newspaper from before Tuesday was created on Tuesday. It just was backdated. Dinosaur bones were created and buried on Tuesday, and
your memories were supplanted, and yada
Yeah.
yada.
oh, I'm sorry, it's Thursday. Otto says it was Thursday. I have the days wrong. That's why it doesn't work. If it was Thursday, it would have worked, right?
That's awesome.
Right. Okay. So yeah, I mean, that's where I come from on the things like two-way speed of light. And it's just imagining it seems, the idea that outgoing light and incoming light are different speeds would have to presume that light is based on yourself. Like the motion of light distant from you varies its behavior based on you. So you're gonna have to go like full on simulation theory to even make that be a thing, right? I mean, how could light going away from me and light coming towards me be different in a world that has anyone other than me?
No, I hear you. I hear you.
You know, and I was just like, no,
and you started
dude.
getting into questions of perception with that too, which is also interesting. Yeah, and pretty loaded.
Okay, did we ever get your channel in here?
Oh, did you ever drop it, Alan?
I did link it in the chat. I can link it in the
Oh, did you put it in the Discord chat?
No, I put it in the YouTube chat. But I just put it in the private. If you can link it for me.
Oh, okay. There he is. It showed up in the private. Yeah, I think it may. YouTube probably blocks links by default.
You can also, it's easy to remember. You go to ethercosmology.com, AETHER cosmology.com. You can find the links there.
So there you go.
Sweet.
All right. There you go. So yeah, the question we started with was, and I had said Michael Morley. So yeah, I've seen it done in person. I've seen videos, and now we don't even do that anymore. We use resonance nowadays for a much higher.
Yeah, 2015 they used resonance, and then they used a error weighted least, or what is it, there's like a weighted regression model against the results of that they had to use. They had to use daily fluctuations and seasonal variance in the model of the actual measurements that they took. So they didn't actually look at the experimentational evidence or the experimentational data, but they looked at the experimentational data through the lens of statistical analysis, reifying the predictions of special relativity.
No, I'm going to just say no. I mean, right. That's going to be your point of view on it.
I would love to see your analysis on that as well.
Statistical analysis is definitely required of experimental data, and that's not a reification
of testing the velocity of light.
Yes, statistical analysis. You do lots of experiments, lots of runs, and you do a statistical analysis over those runs to ascertain what is noise and what is signal.
Yeah, but that specific regression model actually throws out the largest weighted errors.
Okay, and that's just a statement that you're just making here.
I mean, I can pull the paper up.
It would require.
Can I pull the paper up?
I don't think we're ready
to do this right now.
Like on the spot, looking at papers.
Yeah, I don't want to get it. I'm sorry, man. I'm sorry.
Pick one. We'll pick one paper.
I appreciate you having us on. Yeah.
Right. I could also pick out all kinds of papers and throw them at you, and you wouldn't be prepared. That's not what we're gonna do.
Yeah, it's all good. It's all good, man.
So the most recent that I'm aware of verification of the constancy of the speed of light model comes from the Galileo satellites. Was it 2016? If anybody remembers, maybe it was in the 2020s. There was a Galileo launch that failed. It didn't get to orbit. It didn't get to the right orbit. And then, rather than just terminate them, they allowed some grad students to use them to verify the speed of light. Actually, I think it was all the way down to GR. They measured GR
nice.
And
they took it down to the GR level.
Yeah.
What's the difference in that, do you think?
Well, GR includes gravitation and accelerations, whereas just SR is assuming like very small effects of those things, or negligible effects.
So
Right.
what does that?
Special
So what is it?
relativity.
I'm sorry. What does that mean in terms of the measurement? You mean it was more precise
Yeah, well, I mean,
because of
they
the
measured, they tested general relativity's predictions and found that it was accurate to within an error bar that was smaller than anyone's error bar before, up to that
Nice.
point. So I think that's, if I remember right, and you guys can correct me if I get this wrong, that they are the current record holders for the smallest error bars on general relativity experiment.
Dude, I heard general relativity has some really small error bars, and I think that
Yeah,
those are the smallest on record.
yeah, it's really crazy small.
Very tiny.
Yeah. So so as far as why do I think that's the case? That's why I think that's the case. And I'll put back to you guys. How would we test it? How would we test it?
Well, I would just say I've been trying to find experimental data on that. So if you can share that, I'd be super thrilled to look it over.
Galileo relativity. Type Galileo relativity. That ought to do it.
Cool. I will look it over later on.
What else? Do you guys have another one? Yeah, test it. How would we test it? Like, how would we test it? We could presumably build our own, or really just acquire some kind of laser interferometers or something. I mean, obviously, I guess a ring laser, based on what this topic is all about, a ring laser wouldn't convince anybody, right? That's consistent now with what you guys are putting forth, that a ring laser will spin, right?
Mm-hmm. It will spin, yes.
And we're thinking that it could be the rotation of the ether, and I just presented the model of how that could be. So
much appreciated. So
that's cool. A Michelson-Morley interferometer, though, our model, the mainstream model, says it should not pick up anything. Well, I mean, maybe a really good one will pick up the rotation of the Earth, but that's it, right? And you guys are saying no, it should pick up something, right? And
it does. It does.
You're saying it does. Yeah. So would is that a reasonable thing to do, to acquire or build one?
Well, I think it's been done a bunch already. It's just we have varying interpretations of it really at this point. So I don't think that it would satisfy either of us in that regard. But that's my kind of thoughts on it. I think it would be cool.
Why wouldn't it satisfy us? I mean, how do we interpret? Yeah, explain that to me. How do we interpret it different?
So you interpret the Michelson-Morley as as the constant speed of light through the transformation of Lorentz transformations, right? Because there was a variance, but they used the Lorentz transformation to. No.
I would not say that. I would say they measured noise. They measured something, but it wasn't as much as predicted, and it was very, very far below what was predicted. Far enough below that it's within the error tolerance of their device.
Yeah. So then they turned around and took that error tolerance there and then built relativity off of that with length contraction and used that as the evidence for it.
No, not precisely. I mean,
it's dead ass what they did in Einstein's own words in his private letters to his wife.
Okay, we can pick apart what happened in history if that's what you want to talk about. But
I mean, it's related to
Lorentz's equations predate the experiment.
Yeah.
So,
and you would think your boy Ein would have cited him in his paper.
So, the Michelson-Morley experiment.
Right.
The Michelson-Morley experiment is not the cause of the Lorentz transformations.
No.
They predate it.
Right. But he took that
correct me if I'm
framework
wrong here.
no, you're correct. He took that
Okay.
framework though, and that's what it's applied to. And they use that to say that you can't measure linear interferometry on that level because there's length contraction. And then
And time contraction,
they did measure a variance, but they answered that variance with
no.
yes.
No. Lorentz, whatever, all of them agreed that we essentially measured zero. And the reason we measured zero is the transformations.
The transformation
The Lorentz contractions explain why we measured zero. They don't make it so that we.
Oh, I see. No, okay, we're having a slight mistalk. Okay, you're right. Okay, so they measured a variance in the speed of light, and in their own paper, they even say, albeit the orbit must be slower than what we had anticipated if we're to accept these results. And then they agreed, okay, we measured nothing, and then from that, the length contraction came. So my bad, you're right. But that it's still super important. There is a variance shown. And then from that, there was Miller who continued it for 30 years, which you guys, not a fan of. And then there was Yuri Galov, Hector Manera, all these people that did their own thing with with orthogonal interferometers and found the same variance. And then, and then Manera was even trying to
They find different variances. They're all different. None of them agree with each other.
So when plotted against sidereal time, they reached their minimum and maximum dimensions. And then the only thing that varied with Manera is he tried to count extra fringes to get the galactic speed to try to get more out of it. So that's the only difference, because you don't count them like that anyway. Because if you did, then your ring laser gyros and shit would be off, because that's because the way Manera was trying to interpret his results, he was counting more fringes than he should have, so that he could add more speed to it. And I'm saying that he measured the same thing as everyone else did, but his interpretation, that's why he got a differing speed, but it was the same. He was just trying to get more out of it.
Okay. So what you're proposing is that everyone who's done this experiment all gets consistent results. And if we looked at their raw data, we should be able to see the consistency of those results.
Yeah. When you plot it against
and I'm saying that's not the case, because the vast majority, the ones you are not quoting, all say they get zero.
Those are what I'm looking for.
That's the vast majority. Those are the ones you see.
Please provide them. I'm looking for them. So if you got them,
yeah. So when you look at them. So when you get into
start at Wikipedia, you guys start at Wikipedia.
No, I have though. When you get into the modern ones though, if you've read Miller's work, he's the guy that kind of pioneered the calibration of an interferometer. And he found that when you change the sensor location, the length of the arms, the medium in which the light's propagating in, all of those give varying results that change it. Yeah. And so you could and he found,
which is not consistent with anyone, including his or yours interpretation or model, right? And that should tell you the key, which is the error bars are bigger than his signal. If you've looked at his raw data, and I have looked at Miller's raw data, it's really, really noisy. It's very bad. Mm-hmm. So what he did was he took a lot of data, a lot. He recognized that his errors were bad. And so what he did was he took a lot of data and then sort of averaged it out to get his results. That's where his results come from. Any dispute on that? Do we agree?
So he did several analyses of it and varying, applying different weights and stuff to it, and got the same thing. Which obviously, if you're doing that on your own data set, I could see how you're not going to take that as proof or whatever. But there was another one done by James Demio, and there was one done by Maurice Elias that also found the same thing. So when you talk about your what did you analyze in the raw data sets? What did you pull from? You found that it matched diurnal time, or what? Like, what were the inconsistencies that you looked at?
I showed you a curve. I mean, I had it at some point.
That was the curve from his actual paper.
His raw data of one run, just of one run. And one run for him would have just been rotating the device a few times around the circle. And so this is not over days or months or years. It's just over minutes, hours. And his data shows just a massive downward trend in the fringe rate over time through multiple cycles of rotation. And nobody's model has that in it. So that is recognized to be systematic error by everyone, as far as I know, right? Like imagine you measured, I measured a bias in the ether. The ether is moving 10 miles per hour that way. But if I just hold my device still for 10 minutes, now it's moving 8 miles per hour that way. That doesn't make sense in anybody's model. So the only conclusion is that's an error that you're measuring, right?
I see what you're saying. Now, depending on what his measurement apparatus, like how sensitive it was to heat, and if it, if the heat in the room changed. But so I'm seeing a little bit of like a flaw in logic, and I just want you to clarify. So you seem to be indicating that his result set or his analysis used some kind of statistical analysis of a large data set.
Yes.
So why is that okay in this case, or is that not okay in this case? But then in 2015, when they use an error-weighted least squares regression, that is okay.
That's what you do. It is okay. It is correct to do a statistical analysis of your data.
That word gets me every time.
That's a tough one. The thing about Miller was the methods of his day. He followed the proper methods of his day, which was to take an average. And it was understood that that would give you the right result. For nowadays, we understand, no, it doesn't necessarily, because there could be a systematic thing, such as what I'm saying. When you see in the signal a systematic error, you know for a fact that taking the average is not going to give you the correct answer. And we have to go in a little bit more advanced. And if you do that with Miller's data, the signal goes right away. If you use modern approaches, Miller's data is rock zero.
Like I know with like a ring laser gyro, as it runs, it heats up. So as the device heats up, the reading itself that you're taking is going to change, right?
Yeah, that's a good example. And that was something that Miller argued about in his data.
So you wouldn't then throw out all the ring laser gyro experiments, right? You would then instead, you would look at what that fluctuation causes to the data, and then you would take that fluctuation, and then you would, you probably would average out, you could theoretically average out, your run from the start to the end, and then you could, it'd probably be better to look at what it is at the different temperatures. But you get what I'm saying, right? Like there are sensible ways to do that, and I agree with that. Specifically with the 2015 paper, what bothered me about that is that they're talking about daily variations and seasonal fluctuations, which goes hand in hand with what Miller actually purported to have measured. So why would they have to use error regression based on those specific fluctuations?
I don't know. I'll tell you, as far as I personally got with it, and that'll tell you where my head is at. Personally, I looked at Miller's stuff. I researched what several people had to say about it. And then I looked at some of his data and made my own judgment, which was that this data is crap. It's unusable. And I was done. At that point, I'm like, anybody who says that this data is good, I don't buy it. And that's as far as I really went with Miller.
So would you be interested in looking in some modern reproductions of Miller's work? Because I agree, maybe he had like that old interferometer, that old analysis set up. Like, would you like to see what the Russian guy Yuri Galev did?
I mean, maybe I'll look at it. Sure. I mean, I'll look at it. Right. Pick one thing. Like I said, pick one thing.
Yeah. Well, I know we got a broad spectrum of stuff to go over, but I'm just interested.
I was in the classroom. I saw it done. It doesn't. Right. It doesn't, guys. Right. I don't know what you're talking about.
Hector Manera did it in a classroom too, and matched Miller's data too. So like, who knows what happens, man? So that's why. That's why I want you to take a look at it and just see what's up. Like maybe he fucked up, and you could point some major flaw at it. Like I don't know. That's why we're here, bro.
Sure.
Oh yeah.
Cool. Okay. Anything else, you guys?
No, that's it, man. Thank you. This is great.
All right. Cool. Yeah, I guess I should say, like before we wrap up, we're talking about like ether and whether there's an ether and an ether drift and is it whatever. Wouldn't it be a whole lot easier to just determine the shape of the Earth first and then talk about like lasers and ether and stuff?
Oh, dude, the conversations evolved so far beyond flat Earth. Like what? Like
I mean, because none of
like-
these guys, Miller and all of them, none of them are flat earthers, right? Literally zero.
Well, the ether
doesn't
conversation is more about motion and relative motion than it is really about the shape of the Earth, right? Like I said at the beginning, we have Robert Bennett over at Ether Cosmology, and he's actually a geocentrist, but he believes in the globe model of a geocentric model. It's kind of his own thing, but
Okay.
but yeah. So
but, but he believes.
So I would say
he believes the Earth, the sun is like 93 million miles away. But
no, he has his own. He has his own cylinder. His celestial. It's like a celestial cylinder that goes around. It's interesting. With a what did he call it? A like an ether that kind of emanates out from the middle of the center point of the Earth. But in any case, my point being, really, it's not so much about shape, but maybe just motion, right? Relative motion. That's what we're trying to get to the bottom of. And that's why, to me, the constancy of the speed of light is so important, because when we get back to where they measured the relative motion and when they made their decisions about how we measured relative motion, that's where this, this forced the invariance of the speed of light comes from.
My understanding is it comes from Maxwell's equations, actually.
That space-time warps around the speed of light?
No, it's the maximum speed of the the speed of
go ahead. Go Alan.
I was gonna say the what is it? The magnetic permeability and the magnetic permeativity or whatever set in the equations dictates how fast it would be in a vacuum. But there is impedance in the equation, so there is obviously something there, but it's like their interpretation is that it's so minuscule that it must be nothing. Right?
No.
Is that not
it? There. It's the permittivity of free space, right? It's non-zero.
No. I'm sorry. I was applying that to like the vacuum of space, and like the vacuum is empty, but obviously there's a permeativity and permeability in the equation.
Why is that? Has been a puzzle for the ages, definitely.
Indeed.
Why should space present any kind of
as they say, right?
I don't know.
What weird. How doth I get the impedance, right? So,
but we measure it, right? It's there.
Indeed. Very cool.
Okay. That's cool. Let me ask you guys this one then before we split up. If I say Galilean relativity or Newtonian relativity, you guys are on board, right?
Galilean relativity. So Galilean velocity addition. Is that what you're...
Toby, you're saying no? Or you don't know what I'm talking about? I mean...
So you're talking Galileo. you make me... I'm thinking of Newton's bucket, or I'm thinking back to Galileo and...
Aristotle.
Galileo and Aristotle. Like, you should be... Yeah, the boat. You should be able to actually... I actually would agree with the teacher on this one, where if you go to the top of the boat and you drop something, there should be a relative motion that's then translated down to the ground as that item falls.
And it's purely relative, though, is the key. I mean, essentially, you can ride on an airplane, you could pour a cup of coffee, and the coffee doesn't fly to the back of the airplane or anything. It's just like, boop, just the same as you poured a cup of coffee here on the surface of the Earth.
I'm familiar with the concept,
And you guys are with me on that, right? It's like we can create a frame of reference on a moving airplane where everything is static, we're all still, all forces, all accelerations work as if the plane is standing still.
Well, there would be measurable, there'd be ways to measure velocity, in my opinion. That's like why I think that reon wings work is important. I also just in that particular case, there are still going to be dynamic effects, pockets of air that you travel through where the plane's going to bump.
Inside the plane?
Yes. That's called turbulence, right?
Turbulence inside the plane?
You experience the effects of turbulence inside the plane.
Well, the plane vibrates and stuff. Is that what you mean?
Yeah.
Well, those are accelerations. Yeah, we feel those.
Yeah, they're dynamic deviations of the acceleration that that your body is accustomed to, right? So you can feel them. Your body measures them, right? So in my argument would be that that there should be a detectable motion uh within that reference frame. There's usually going to be some kind of dynamic effect, like as explained with Newton's bucket, right? Although the person within the bucket sees it as stationary, that doesn't mean that there's not a dynamic effect of whirlpooling happening. That's an effect of the of the of the motion.
Okay, but an airplane doesn't. In linear motion, we don't get that. The bucket is a rotational motion, and we do. And I'm with Newton on that one. That when we rotate, there is clearly a visible effect, a measurable effect caused by the rotation. But when we move at a constant linear speed, there is no measurable effect that we are aware of. Although it sounds like you guys want to say that light will provide that for us, even though sound does not, coffee does not, bouncing a ball does not, walking to the bathroom on the airplane does not. None of those things create a measurable effect, but maybe light could. Is that what you're saying?
Shout out to Ruyong Wang.
Yeah, I guess so. Yeah, just Ruyong Wang, I guess. Yeah.
Okay. Does that statement in itself give you pause at all? Because that's really what sparked Einstein to think that way, was nothing else matters. Why would light suddenly matter? Because electronics, they work on the airplane, right? They work at thousands of miles per hour, evidently.
Yeah, but shout out Bennett's hiker. If you are if you are moving relative to another object, there's going to be a translation of motion. There's going to be dynamic effects. There's never been a demonstrable experimentational proof of any kind of orbital motion.
What?
Yeah.
Okay. I mean,
you can go back to
other than the devices that orbit, right?
You talking about, so in that case, you're just scaling off of Kepler's third law, right? You're just going off of a one scaling equation. That's you're reifying Kepler's third law in that case, if you're going to try and go that route.
No, I just satellites and stuff, right? I watch them go around. They go around.
Well, yeah, they're up. There are items in the sky that are following a certain pattern, indeed.
Okay.
Yeah,
okay.
Yeah.
So that's not an orbit.
I mean, orbit is a very particular word, and you know that on my model that we wouldn't. You could maybe retroactively call it an orbit because of the old paradigm that many of us are familiar with. You could call it an orbit, but it's not orbiting anything. It's actually matching a toroidal pattern that emanates out from the center. It's interesting actually when you look at what the patterns of the satellites are over a flat Earth model, and you see that they make very interesting patterns. Yeah, which, as you understand, it would as you showed us with your globe that you pulled out, like obviously you're going to get interesting patterns. But yeah, so that's where me and Alan are saying, like this could be like a vortex that we're seeing here, or some kind of a toroidal, a toroidal shape that's manifesting these things.
Okay, that's a really interesting approach. And I think maybe it's sort of consistent with that. Was it Martin, the guy that we were talking about? Marsden Martin, something? Whatever. That guy, is that he's not saying we don't measure what we measure. He's saying there's no reason we measure what we measure. And maybe that's what you guys are saying now. Like a satellite, it's up there, it's moving, we can track its pattern. Maybe it's up there for real, and that there's just some force pushing it to go in this sine wave around a circle. That
there could be like a especially emergent phenomena of an ether flow at those high altitudes.
Is it possible then that that I'm going to call it gravity for lack of a better word, that there is a force pulling objects but it's not towards a center of a globe, but it's towards that pattern. That's what the shape of the force is. That basically we take, like we took the ether flow when we unwrapped the globe, we could unwrap gravity and say that gravity is doing that up high. Gravity is not pulling down anymore, but is in fact pulling things.
No. I'm not gonna say that they're not using balloons or they don't have some kind of propulsion or something like that to get up there, right? They have to launch the satellites into space, even on your model. So I'm not disputing that. What I'm saying is that once you're up there and you have, you know, a lower level of ground, this is just pure speculation. You know, lower level of interference from ground activity, that there may be actually just a more uniform flow of ether that's not as inhibited by the ground. That's just totally me, you know, spitballing. But either way, they could also be using propulsion. They could also be, you know, following some kind of weather pattern. They could be using solar. You know, like, to me, the ISS is easy to explain. Yes, it's something that I would observe, but, you know, it has solar panels on it. And why wouldn't they have a base in the sky, right? That's something that just makes perfect sense from a military point of view.
A military base?
Yeah, or even just from a global monitoring point of view. Why wouldn't you want to have a base in the sky?
What do you mean by base? Like maybe somewhere we could watch the Russians from?
Or just like what you know is known as the International Space Station. You know, there's definitely something up there, is what I'm saying. Yeah.
Why do what military do you want to put up there? Is what I'm asking.
Well, there's a bunch of government authorities up there. There's a bunch of astronauts that they say go up there, right?
Sure.
So there's some. I don't have any. I don't know the chain of custody on that documentation. I don't know, you know, who's what, who signed what. I don't know that.
Okay. Yeah. Cool. All right. Let's do this. Let's pick one thing. You guys mentioned a few things for me to look at. What do you want me to look at? Pick one. I started with that one, and I'm planning to do that. And if you're ready to talk about it soon, I would love to have you guys come back and talk about it. It was, remind me again. I'm going to look it up while we're talking here.
Yellow?
No, it was of those papers you sent me.
Paul Marmot.
Marmot. That sounds right. So I knew it started with an M. I am so bad at names.
Marmot, I think, actually. There's a guy named Doug Marmot that I get confused with.
If I can find it. Marmot. Let's look for Marm. No, I'm not finding it.
Second, bro. I got you.
Man, I'm just so bad at names. I'm in the wrong channel. That's why. Why. No results. Okay, fine. How about
I put it in the chat.
Okay. Bring it back. Yeah, that's the one, Marmot. That's it. The GPS and the constant velocity of light. So yeah, that's the one I want to look at next. And if you guys want to be around for that, we can talk about it and
cool. Oh, yeah.
And look at what does it say? What does it not say? Is it right? Is it wrong? Is it different from mainstream science? All these questions.
Absolutely, man.
All right, that'd be cool. All right, yeah, and I'm gonna say the same thing I always say, which is, you know, there's a lot easier stuff we can do. Super easy stuff we can do to determine the shape of the Earth. We don't need any of this.
Yeah.
But that's not what you guys are into. You guys are into this. So, all right, cool. Anything else, you guys? You want last words?
No, that's it, man. Thanks for having us on. Appreciate it. You've been awesome. I send people to there's two globe proponent people that I send people to. It's you and Parks. You guys answer questions and give, you know.
Yeah.
Oh yeah, the old predatory publisher. Yeah,
it is. But I mean, I'm gonna counter on behalf of the guests with the obvious counter, which is that peer review wouldn't publish fringe. The peers will shoot it down, and we usually do. It's true. I mean, I would have shot it down. I like, no, I'm not publishing this. So what are you going to do, right? If you're Mr. Fringe, you're going to have to go somewhere else.
Yeah, absolutely. So shout out to Attica Scientific for hosting them for giving those people an outlet. Very nice. All right, cool.
All right.
Thanks, man.
Later, guys.
Thanks a bunch, Matt. This was awesome.
Have a good night, bro. Peace.
Good night.